So welcome to Unit 6 in CS373, Programming a Robotic Car. This is the final unit focused on putting it all together. Let's review some of the things you learned. You learned about localization, tracking, planning and control. And you also learned about probabilities, so-called filters. You learned about A star, dynamic programming, DP, and about PID control. There's a lot of stuff, and you implemented quite a bit. So today, we take all those pieces and we put them together to build a true robotic self-driving car. Let's start with localize.
You have learned so much already, and you should be so proud of yourself. If you've made it this far through AI for Robotics, then you have the skills to complete the nanodegree program, run your code on Carla, and get a job in the autonomous vehicle industry. Don't stop, keep going. See you in the nanodegree program.
We learned about how maps are being used to localize a moving robot. Here's a laser map being produced, in this case Stanford's car. And we used particles to localize this robot by matching momentary measurements with the previously acquired map. In doing so, we were able to localize Junior in the DARPA Urban Challenge with centimeter precision. A similar method is being used by the Google Street View car, and it is one of the secret sources of the Street View car. We heavily rely on a previously built map and the type localization method that you implemented to localize the robot and make it follow known lanes. So here's a localization quiz. We learned about the three filters: Kalman filters, histogram filters in our first class, and particle filters. Check the corresponding box if the attribute applies. So if any of those is multimodal in their distributions, please check the box. Exponential in the computational complexity relative to the number of dimensions, and useful in the context of robotics. Please check none, any, or all of those boxes. And of course, we learned that the Kalman filter is unimodal, just a single bump, whereas histograms and particles can have multiple bumps. The Kalman filter was more efficient than the histogram and the particles, that both require exponentially many units in the number of dimensions in the worst case. And yes, my God, they're all extremely useful. Super, super useful, in case you didn't get this from the class. We also learned about planning, in particular breadth-first planning, A-star planning, and dynamic programming planning that all address slightly different use cases. And those are being used to plan the trajectory of the Google Street View car and the DARPA Grand Challenge cars. In fact, you implemented a good number of those, which is quite amazing. So here's my quiz for planning. You learn about breadth first, A-star, dynamic programming. And for the sake of this comparison, I also include the smoother, which is more like plan refinement. Check any out of or all of those boxes if the corresponding planner acts in a continuous space, if it finds an optimal solution, if it's a universal plan, that means the solution once found can be applied to arbitrary states, or if the solution is local, which means given an approximate initial solution, it cannot really do anything more than just locally refine the solution. Smoothing was the only planner that actually really worked in a continuous domain. Everything else was very discrete. Now breadth, first, A-star, and dynamic programming all find the optimal solution. Dynamic programming is the only one that's universal. And smoothing is the only local operations, whereas those over here all optimize a global planning problem. And then we also learned about control. You implemented your first controller. Control is what makes things like the following experiment possible. So here's my quiz. We learned about PID control, and specifically the P term, the I term, and the D term. Which of the terms is most associated with the idea of avoiding overshoot, minimizing error relative to a reference trajectory, and compensating drift? I want you to check exactly one checkbox for P and one for I and one for D. The primary function of P is to minimize the error. You steer in proportion to the error. The D term avoids the overshoot if used wisely. And systematic drift and biases are best addressed by the I term. So that's the correct answer, which I'm sure you got right at this point. So now let's put them all together into a single piece of software. Now up front, it took me about a whole day to do this. So I'm not going to ask you to do it all yourself, because it's going to cost you probably at least an hour if it takes me a day. But I still want to be able to take all the lessons that we did together into a single system. So I want to help you a little bit, bits and pieces. But up front, here is the environment that I wrote for you, which is very much derived from the environment we studied in the past. We have a class robot that has certain kind of noise characteristics you can find over here. And as I scroll down, you can see the familiar init function, the position setting function, the set noise function. And then we have two checking functions, whether we have a collision with a world called grid, which I'll show you in a minute. And we have a check goal function to see if we reached a goal according to a certain distance threshold. The move function should be very familiar at this point. It applies noise to the motion command. It's the same code that you originally wrote. And then we have a very simple sense function, which measures the robot's XY location similar to a GPS on a car, but with substantial measurement noise. Corresponding to this sense function, we have a measurement probability function that you might want to use in your filter, and that evaluates the probability of a measurement relative to the ground truth coordinates of the robot using Gaussians. Armed with all this, here is the problem. I'm going to give you a grid. Here's an example grid. Let me draw this for you. This specific one happens to be of dimension 6 and 5. And there are a number of blocked off cells like this. And if you look carefully into the code, you'll find information about the initial starting location on the left upper corner and the goal location, which is the bottom right corner. So in putting everything together, we're going to build a robotic car using our bicycle model. They'll drive through the free space, through the continuous free space, on something close to the shortest path, all the way into the goal. So here is my solution that I implemented, and that you will get to see for most parts towards the end of this class. I'm starting up over here. These are my obstacles. They implemented as circles to the center of these grid cells. Not exactly correct, but good enough for my implementation. And here are multiple runs using the same code. And you can see they're far from optimal. They are non-optimal because there's control noise and there's also measurement noise. But they all make it safely through free space into the corner where the goal objective is. If you look at them in detail, like this solution over here, you'll find that the spacing of the circles is somewhat variable. You'll find that there's little corners over here that are either the result of control noise or of measurement noise or of my somewhat deficient implementation. And you also find the control set points that are the smooth points of my A-star planner, as shown here in green. In the version that I implemented for you, the controller does something very, very different. It actually chooses as the control objective to head straight to the goal using the A102 function, executes the action at a speed of 0.1, and then reports a collision whenever the robot is moving. And just looking down to the output, where we see the robot's coordinates along with the orientation, there's very frequent collisions that the robot undergoes in its attempt to reach the goal, which it eventually does, but you can see two big regions of collisions until the goal is finally reached. So I spent a couple of hours porting all the code over into this new format, and I want to spare you all this editing work. So in the final code, that is a little bit incomplete still, we have a grid. We run a function called main. Main then runs a path planner, A star, smooths it, and then runs a controller, as in run. And in the controller, I even implemented for you our particle filter that you're familiar with. There's nothing new here. You're running the exact same code from class that you programmed yourself. And then I go through a loop where I compute a cross-tag error, apply my only PD controller, there's no I term here, and I run my particle filter as before to estimate where the robot is. What I would like you to do is to implement the cross-track error function. And I want you to use as an input the estimate, not the actual robot position, but the best estimate, which we can get by running filter.getPosition. Now here is the difficulty. And I can tell you confidently, it took me more than an hour to solve this problem myself, just for this class. Our path now is a sequence of linear pieces. When a robot drives along, it has a certain cross-track error. But as the robot state projects beyond the end of a line segment, as is happening here, we have to change the corresponding line segments to be the next one. So in addition to calculating the signed error relative to an arbitrary line segment, not just the y-axis, we also have to detect when the robot steps beyond the end of a line segment and switch over to the next one. Now suppose this is our line segment, and the path is given by the coordinates of the beginning point, P1, and the end point, P2, both of which are xy coordinates, which you get straight in the path. Suppose our robot's position is something like this, where it has its own xy estimate that comes out of the particle filter in your case, and it has its own orientation, theta. Then both the cross-track error, as well as how far it's progressed along the line segment, call this u, can be calculated using a dot product. Specifically, let's call this vector over here delta x and delta y, as defined in x2 minus x1 and y2 minus y1, this vector over here. And let's call this vector over here rx, which is x minus x1, and ry. Then u, the ratio of how far we've progressed along the segment, is given by the dot product rx times delta x plus ry times delta y divided over the sum of squares delta x times delta x plus delta y times delta y. Why? Well, this normalizes the vector length to 1, and this is the dot product of this vector over here and the green vector, which happens to define the distance. So if this is larger than 1, we know we've left the segment. It's time to move on to the next one. Finally, the cross-track error, the red one over here, is given by a similar but not identical dot product of ry times delta x. Notice we're now multiplying a y with an x, minus, instead of plus, rx times delta y, with the exact same normalizer as down here. So you can see the normalizer over here. So what I want you to implement is this piece of math over here. When you run your controller, you will find that I set up for you a variable called index. That's the index into your path. When u exceeds 1, we should increment this index. Make sure it never goes beyond what's legal in path length. And the cross-track error should be computed relative to the current index, and is of course a signed error using the exact same dot product I've shown you. The last thing I want to tell you is what the path is, and I want you to use the following path. The path is called sPath. It's given, the run function is one of the parameters over here. You can see this up here. So sPath index is the indexed element of this path, and 0 stands for x and 1 stands for y. So please fill in the missing code over here. And I should tell you, when you run our controller with the missing code included, you get actually a valid, nice path that mostly doesn't collide. Occasionally does because of randomness in the system, but it should be mostly collision free. And for this example, require about 130 or so robot steps. And just so that you see a typical answer, here is a random run, which means, and you read this as follows: true means the robot actually found the goal, 0 means 0 collisions, and it took 137 steps. Let me run it again. And here's another outcome. Robot didn't collide. It reached the goal in 145 steps. I should warn you, sometimes I do get collisions here, and it's because our obstacle circles are relatively large. The noise in the system makes it hard to navigate. But most of the time you should be able to get to the goal without difficulties if you implement this piece of code correctly. And just to warn you, it took me quite a while to work this out. So here's my code. I compute the dx and dy the way I told you by using the sPath of index I plus 1 minus the same at index. My rx and ry called drx and dry over here, are the robot estimates as obtained by the filter minus the path. And then I apply the exact same two equations that I gave you for the progress U and the cross-track error CTE as shown over here. And of course, if I'm advanced too much, I add 1 to the index. You could have done this before computing the cross-track error, but I chose to do afterwards. And when I run it, I get sometimes a collision. There's 2 collisions here, but I still reach the goal in 140 steps. Let me run it again, and now I reach the goal without collision. So in the final question, I'd like to explore something, and I don't have a good answer for this, but I'd like you to play with those parameters over here. The data weight, this weight smoother, the control parameters p gain and d gain. Play with them, try to find a setting that gives me fewer collisions on average than my current parameters, and maybe reaches the goal even faster. I should warn you, these are about the best values I would find, but I didn't really apply twiddle to this. I did more than an approximate investigation of what a good parameter might be. When you apply twiddle and try this, you will find that it's hard to apply because your function might never return, so you have to build in a timeout somehow. But it's fun, play with those and see if you can find a better solution than what I gave you. If you do so, don't expect a correct answer from me. I didn't implement it myself, but I want to give you the opportunity to play with those parameters and see what the effects are on the solution. So this finishes the lecture part of CS373, my basic introduction to robotic AI. And even though we haven't done the final exam yet, I want to congratulate you for getting this far. The fact that you got this far means that you really likely a very amazing student. You put a lot of work into this, I know this. It took me a lot of work to make those classes, but it probably took you even more to digest them. I hope you learned a lot and had a lot of fun, and you feel empowered to program robots better than before. What I taught you, I believe, is the very basic set of methods that any roboticist should know about programming any robot intelligently. All of those robots have tracking problems, state estimation problems, planning problems, and control problems, be it a surgical robot, be it a robot maid, or your intelligent future household robot, or even a flying robot, such an autonomous plane. So I want to thank you for being with us so far. The rest of this unit contains extra information on SLAM. Otherwise, I'll just see you in the final. Hi students, I'm back to teach you a bit about SLAM. There was a request, popular request actually in email and discussion forum. So SLAM is a method for mapping. It's short for simultaneous localization and mapping. And some of this might show up in the final exam, so do pay attention. Mapping is all about building maps of the environment. You might remember in the localization classes, we assumed a map was given. One of my big passions in my life has been to understand how to make a robot make these maps, like this map over here, which is a 3D map of an abandoned underground coal mine in Pennsylvania near Carnegie Mellon University. Over the past 10 years or so, I've worked on a number of different methods for building maps that are quite sophisticated, like this particle builder method over here that you can see. And all these maps have in common that we build a model of the environment, while also addressing the fact that the robot itself accrues uncertainty while it moves. So when, in this example here, the loop is being closed, you can see how our mapping technology is able to accommodate this and find a consistent map despite the fact that the robot drifted along the way. So the key insight in building maps is that the robot itself might lose track of where it is by virtue of its motion uncertainty. We accommodated this in localization by using the existing map, but now we don't have an existing map, we're building the map. That's why SLAM comes into play. SLAM doesn't stand for slamming a robot. What it really means is simultaneous localization and mapping. This is a big research field. Most of my AI book is about this technology. And today I want to show you my favorite method called GraphSlam, which is also by far the easiest method to understand. We will reduce the mapping problem to a couple of very intuitive additions into a big matrix and a vector, and that's it. Here's a quick quiz. When mapping an environment with a mobile robot, uncertainty in robot motion forces us to also perform localization. And I only give you two possible answers, yes and no. And the answer is yes. In nearly all cases of mapping, we have robot uncertainty in motion. That uncertainty might grow over time. We need to address this, otherwise the map looks really bad. Let me give an example. Suppose a robot drives down a corridor and it senses surrounding walls. If this robot has a drift problem, and because of its uncertainty in its motion, it actually believes it drives a trajectory like this, then the surrounding map would look very much like that. Now, these might be indistinguishable at first glance, but if this robot ever comes back to the same place, then there's an opportunity to correct all this. So a good SLAM technique is able to understand not just the fact the environment is uncertain, but also the robot itself runs on an uncertain trajectory. That makes it hard. So let me take you about my favorite methods of all, called graph SLAM. This is one of many methods for SLAM, and that's the one that's by far the easiest to explain. Let's assume we have a robot, and let's call arbitrarily the initial location x equals 0 and y equals 0. For this example, we just assume the robot has a perfect compass and we don't care about heading direction, just to keep things simple. And let's assume the robot moves to the right in x direction by 10. So it's now over here. In a perfect world, you would know that x1, the location after motion, is the same as x0 plus 10, and y1 is the same as y0. But we learned from our various robotic Kalman filter lessons and others that the location is actually uncertain. So rather than assuming in our xy coordinate system the robot moved to the right by 10 exactly, we know that the actual location is a Gaussian centered around 10, 0, but it's possible the robot is somewhere else. Remember, we worked out the math for this Gaussian? Here's how it looks like, just for the x variable. Rather than setting x1 to x0 plus 10, we try to express a Gaussian that peaks when these two things are the same. So if you subtract from x1, x0 and 10, put this into a square format, and turn this into a Gaussian, we get a probability distribution that relates x1 and x0. We can do the same for y, and since there's no change in y according to our motion, all we ask is that y1 and y0 are as close together as possible. The product of these two Gaussians is now our constraint. We wish to maximize the likelihood of the position x1 given that the position x0 is 0, 0. So what graph SLAM does is defining our probabilities using a sequence of such constraints. Say we have a robot that moves in some space, and each location is now characterized by a vector x0 and a vector x1, vector x2, and vector x3. Often they're three-dimensional vectors. Then what graph SLAM collects is the initial location, which is just 0, 0, 0 usually, although here it looks a little bit different. And then, really importantly, lots of relative constraints that relate each robot pose to the previous robot pose. We call them relative motion constraints. You can think of those as rubber bands. In expectation, this rubber band will be exactly the motion the robot sensed or commanded. But in reality, it might have to bend it a little bit to make the map more consistent. And speaking about maps, let's use landmarks as an example. So suppose there's a landmark out here, and the landmark is being seen from the robot with some relative measurement. 0, z1. Perhaps it didn't even see it during time 2, but then this is z3. All these are also relative constraints, very much like the ones before. Again, they're captured by Gaussians, and we get relative measurement constraints. One such constraint every time the robot sees a landmark. So graph SLAM collects those constraints, and as we'll see, they're insanely easy to collect. And it just relaxes the set of rubber bands to find the most likely configuration of robot path along with the location of landmarks. And that is the mapping process. Let me ask you a quick quiz that'll take some thinking. Suppose we have 6 robot poses, that is 1 initial and 5 motions, and we have 8 measurements of landmarks that we've seen. These might be multiple landmarks, sometimes the robot saw more than one. The question now is, how many total constraints do we have if we count each of these constraints for exactly one constraint? And the answer is 14. There's 1 initial location constraint, 5 motions, which adds up to 6, and 8 landmark constraints. So that's the gist of what we're going to implement. The key insight now is that this is insanely simple to do. What we do is we make a matrix and also a vector. and we label the matrix, which is quadratic, with all the poses and all the landmarks. And here we assume the landmarks are distinguishable. And every time we make an observation, say between two poses, they become little additions locally in the 4 elements in the matrix defined over those poses. So for example, if the robot moves from x0 to x1, and we therefore believe x1 should be the same as x0, say plus 5. The way we enter this into the matrix is in 2 ways. First, 1 x0 minus 1 x1s added together should be, well, minus 5. So we look in the equation here, x0 minus x1 equals minus 5. These are added into the matrix that starts with 0 everywhere. And it's a constraint that relates x0 and x1 by minus 5. It's that simple. Secondly, we do the same with x1 as positive, so we add 1 over here. And for that, x1 minus x0 equals plus 5. So you put 5 over here and a minus 1 over here. Put differently, the motion constraint that relates x0 to x1 by the motion of 5 has modified incrementally by adding values the matrix for all elements that fall between x0 and x1. We basically wrote that constraint twice. In both cases, we made sure the diagonal element was positive, and then we wrote the correspondence off-diagonal element as a negative value, and we added the corresponding value on the right side. So let me ask you a question. Suppose we know we go from x1 to x2, and whereas the motion over here was plus 5, so now it's minus 4. So we're moving back in the opposite direction. What would be the new values for the matrix over here? And I give you a hint, they only affect values that occur in the region between x1 and x2 and over here. And remember, these are additive. So here's the answer. Let me just retransform this as I've done over here. x1 minus x2 is now plus 4, and x2 minus x1 is minus 4. So I have to add plus 1 over here, minus 1 over there, plus 1 in this diagonal element over here, and minus 1 over here. Let me just do this. These numbers added in transform the first number over here to 2. We get a minus 1 for the off-diagonal elements, and a 1 over here. And now we add 4 to the 5, which gives us a 9, and a minus 4 to the 0 gives minus 4. So this is where we are now. Let me do another quiz. Suppose at x1 we see landmark L0 at a distance of 9. This gives me a relative constraint between x1 over here and landmark 0, which is over here. So just like before, these link 2 things together relatively, the x1s and the L0. Now this doesn't look like a submatrix by this, it's spread a little bit apart, but I want you to modify those 4 values in the matrix and those 2 values in the vector to accommodate that we believe the location of L0 is 9 greater than the robot position x1. And here's the answer. Obviously x1 minus L0 is minus 9, because L0 minus x1 is our measurement of plus 9. So let's add this in. We add 1 over here on the main diagonal, 1 and 1. We subtract 1 off the main diagonal, just like before, simple pattern. And then the 9 over here goes back to 0, but to 9 over here. I hope this makes perfect sense to you. So let's summarize what we learned in form of a little quiz on GraphSlam. Check this box if GraphSlam seems to be all about local constraints. They require multiplications. If that's true, check the box over here. They require additions. Check this box if this is correct, or none of the above. And the answer is obviously they are all about local constraints. That's the entire point. Every motion ties together 2 locations, and every measurement ties together 1 location with a landmark. Multiplications is just the wrong thing here. So all about additions. So these are the correct things to check. I want to add one last thing here, the initial robot location. If we define x0 to be 0, which is the origin of the map, then what this means is we add 1 over here and 0 over here. And the reason why is this constraint is that x0 is 0. So let's take a robot moving around. And let's see it sees a landmark from the first pose, x0, and from the third pose, x2, but not from the second pose. I want you, in this matrix over here, check mark all the fields that are being modified by GraphSlam, It's a binary check, and the same for the vector, without putting actual numbers in. So go into this matrix and ask yourself which fields will be 0, the ones that are untouched, and which ones will not be 0, that are the ones we modified. And the answer is our initial constraint would touch this guy over here. The 1 to 2nd motion touches these things over here. The 2nd to 3rd, these guys. And then the landmark observation over here puts something between x0 and the landmark that sits here, 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 here again, and here. And this observation over here puts something between x2 and the landmark. These guys over here and the guys over here. And that means we have only the following places that are still 0. And this means there's no direct constraint between x2 and x0. That is, there's no direct motion information between these guys. And there's no direct constraint between x1 and L, which is this guy is missing over here. So let me do the same quiz again. Now we have 2 landmarks. And the picture I'm giving you is a robot with 3 total positions. There's a landmark here and a landmark here. And say this landmark is being seen at these 2 positions and this landmark at these 2 poses. But landmark L1 is not seen at x2 and landmark L2 is not seen at x0. And of the 30 fields over here, how many of them will never be touched? Please put your answer over here. And the correct answer is 6 for the following missing links. This guy here gives me 2 values in the matrix. This guy here, another 2. And this link here is also missing. So it's another 2. So there's 6 values missing. Let's prove it to ourselves. Moving from x0 to x1 fills out this area. From x1 to x2, this area. So seeing landmark L0 from x0 and x1 means we fill these guys over here and the main diagonal there. And seeing the other landmark from x1 and x2 means we fill these guys over here. So let's count the ones that are still open, and here are the ones. And my answer was actually wrong. It's 8. I overlooked. There's no direct link from L1 to L2 either. So my apologies that I gave you the wrong number, but it proves to you this is actually not an easy question. It's harder than I thought. And the reason is there's also no direct link that constrains L1 and L2 directly. Landmarks can't see, so they can't put a direct link between any 2 landmarks. Or put differently, in this part over here, our matrix will always be a diagonal matrix. The last thing I want to tell you before we go into programming is why this makes any sense. Suppose you fill the matrix, which I call omega, and the vector, which I give the Greek name of xi. My apologies to my non-Greek students here. You Greek students should be very proud. You always have a special place in my mathematical heart. Then I can find the best solution for all the landmark position or the wall position by a very simple mathematical trick. And that is completely counterintuitive. I invert the omega, I right multiply with xi, and out comes a vector mu, which gives me the best estimates for all the robot locations and the landmark locations. Now that is quite amazing, because all it means in GraphSlam is that you keep adding numbers to these matrices every time you see a constraint. And when you're done with it, you run a very simple procedure, and out comes the best places for your robot. So let's go and try it. I'm not going to ask you to program this, and I'm giving you my matrix class, so you can do this easily. What I'm asking you to do is to build a 3x3 matrix, and of course a 3x1 vector, by which you shall state that our initial location is -3. x1 in exploitation is obtained by adding 5 to x0, and x2 is obtained by adding 3 to x1. So in expectation, what we should get out, we run the mu equals omega -1 times xi trick, that x0 becomes -3, x1 becomes 2, and x2 becomes 5. So diving straight into our programming environment, I'm giving you a matrix class. You might want to take a moment to look over it. It's a little augmented to what I've given you before, and I fixed a bug with the inversion code, which is quite essential. And if I run it, I construct an omega matrix, piece by piece. That's the one that you should come out with. A xi vector. And then I run and print out, using the show command, the result of omega to the -1 times xi. And you can see -3, 2, and 5 are the correct result. That the result from the omega matrix and xi vector. So what I want you to do is write code that incrementally, step by step, constructs the omega vector and the xi function and then returns to me those results over here. There's an empty function in your code that accepts as parameter the initial position -3 and the two motion values 5 and 3. And here's my result. I construct an omega matrix of size 3 by 3, and initially I set the top left coordinate to 1, and in the vector C I set the very first value to init, everything else is 0. And now come the important additions for the first move and the second move. Both times I do exactly what I told you before. For the two involved variables, I add a +1 on the main diagonal and a -1 off diagonal. Same over here. And then I subtract move and add it one row later. And the same with move 2 over here. Look very carefully. This is exactly what I told you about. I'm going to draw this graphically. I begin with a matrix like this. I then add this guy and then this guy. And as far as the vector is concerned, I start with this, add this guy, and finally this guy. Then these two together are being combined down here, where I compute the inverse of omega multiplied with xi. That gives me the vector res, and res is being output using the show command and returned from the procedure. Now let's add the landmark. And let's say the landmark is being seen at all time steps. Let's say in the very first time, the difference between the position and the landmark is 10. Obviously, this is a one-dimensional example and not two-dimensional as the picture suggests over here. Then it is 5, and then it's 2. Now, what's the landmark position? You can work this out in your head. It's a single number. Please enter it here. And the answer is 7. Obviously, -3 plus 10 is 7. -3 plus 5 plus 5 is 7. -3 plus 5 plus 3 plus 2 is 7. So all of those work out to be 7. We have a fully consistent situation where the landmark is consistently seen. There seems to be no noise whatsoever. So now I want you to extend your routine to accommodate the landmark. And specifically, I want you to use a function that I coded for you that's very useful. That is called expand. So you can run omega.expand and xi.expand to take your 3 by 3 matrix or vector and move it to a 4 by 4 vector that you actually need when you have to include the landmark itself. So give that a try and see if you can modify the code. Now I have additional input parameters of measurement 0, 1, and 2. So in particular, here is our new do-it routine. It now has as input parameters my 2 motion commands and the 3 measurements command for the 3 different poses. Here's the code that you produced here before. That's my version of it, where we have the initial 3 by 3 matrix. And then upon using the expansion command, you can now increase those to a 4 by 4 matrix and 4 by 1 vector. And then when you run it, what comes out is this result over here, -3, 2, 5, and 7. And I want you to do this, where -3 and 2 and 5 is the forward path, and 7, as before, is the landmark location. So please code this and realize that I can modify the input to do it just fine, and your code should not just produce this one vector, but it should implement the right math. And here's my answer. So here's the expand command. It takes the omega vector, turns into a 4 by 4, and assigns the existing coordinates to 0, 1, and 2. And expands my xi vector from 4 to 1, where it uses the previous dimensions to 0, 1, 2, and 0. Now that turns out to make a larger matrix and larger vector. And now I go and add in the measurement constraints. In all of those, I have to relate to the last coordinate, which is my measurement coordinate, from the first, the second, and the third pose. And I have to subtract -z0, 1, and 2 from the corresponding robot poses and add them all up back to the last pose. If you implement this correctly, then you get a omega and xi that once you implement this solution equation gets you the solution over here. Here's a really tricky quiz. Let's look at the robot motion again and say I changed the last measurement from 2 down to 1. You might remember the robot poses were -3, 2, and 5. Before that modification, the landmark position was 7. But a 1 doesn't really add up. A 1 suggests I might be at a different distance to the 7 than the 5 over here that comes from this side. So here's my quiz. First, I want you to know if I make this modification what is the effect on x2? Will the estimate be smaller than 5? That is, we shrink the robot path a little bit. Will it be exactly equals 5 like before? Or will it be larger than 5? Check exactly one of the 3 boxes. And I also want to know what's the effect on x0. Will it be smaller than -3, equals -3, or larger than -3? This is a completely non-trivial quiz. It takes really some thinking. Invest in thinking, and you can even go back and try it out. So I'm trying it out and see what happens. So before it was -3, 2, 5, 7. And now the first position is completely unchanged, and I explain to you in a second why. The third one went from 5 to 5.5, and the landmark went down from 7 to 6.8. So graphically, this guy becomes larger than 5, and this landmark even shifts a little bit to the left to make these two things closer together than they were before when they had a separation distance of 2. Now, this picture doesn't really explain it well because it's a 2D picture, but in 1D, that's exactly what's happening. Also interesting, the initial position is unchanged. So these are the correct answers. Now, I would be blown away if you guessed them correctly. The reason why the initial position doesn't change is the only information we have about the absolute coordinate location is the very first initial position anchor that we said it has to be -3. None of the relative rubber bands change the fact that we nailed this guy to be -3. A relative strength change between these two things over here means the rubber band is different, but it's a relative thing. This is the only absolute constraint we put in. So clearly the absolute location of the first position doesn't change. The reason why it becomes larger than 5 is, well, think about rubber bands. Our landmark is at around 7. We believe to be at position 5 in the noise-free case. But we just put a tighter rubber band between them. It's not 2 anymore. It's now 1. And that means we are inclined to move the landmark and this position closer together. And that's exactly what happens. If you go to the solution over here, the final position becomes 5.5. So it's now 5.5. And the landmark becomes 6.875 instead of 7. Now this is a case where the rubber bands don't add up. And this is one of the places where GraphSlam is just magical. So before, everything ended up, but we have cycles in these structures. And these cycles might not add up because we have noise and motion, noise and measurements. What our method does, by computing this thing, omega to the -1 times c, we find the best solution to the relaxation of those rubber bands. And that to me is sheer magic. I'm going to give you a glimpse as to why it works. Suppose we have two robot positions, x0 and x1, and we know they're 10 apart with some Gaussian noise. But we know that the Gaussian noise in expectation moves the right robot position 10 off the left robot position, but there is some uncertainty. When we talked about Kalman filters, we talked about Gaussians. And this uncertainty might look as follows. There's a constant, exponential, in the expression that x1 minus x0 should relax to 10, but might deviate from it. This Gaussian constraint over here characterizes a constraint between x1 and x0 and wishes them to be exactly 10 apart. The Gaussian is maximum with this equation is fulfilled, but if the residual is not equal to 0, there's still a probability associated with it. Let's now model a second motion. Say x2 is 5 apart. We now get an even bigger Gaussian relative to the very first one. But the local constraint over here reads just like the constraint over there. So let me just write it down. x2 minus x1 minus 5 square over sigma square. Now, the total probability of this entire thing over here is the product of these two things. If we want to maximize the product, we can play a number of interesting tricks. First, the constant has no bearing on the maximum, just on the absolute value. So if we want to find the best values for x0 and x1 and so on, we can drop the constant. Secondly, we can drop the exponential if we're willing to turn the product into an addition. And remember, we added things in omega and in sigma. That's why. And finally, we can actually drop the -1/2. Turns out that also plays no role in the maximization of this expression. So it turns out what you added were constraints just like these, and you even added them with a certain strength of 1 over sigma square. In particular, if you really believe that a constraint is true, you should add a larger value in this matrix over here, And on the right side, you should multiply the right constraint with an even larger value. Put differently, take an expression like this and multiply the sigma square. You get something of this nature over here, where 1 over sigma regulates how confident you are. For a small sigma, 1 over sigma becomes large, so 5 is much larger than 1. That means you have much more confidence. Let's go back to the code and modify the code so that the last measurement has a really high confidence. So I want you to multiply the last measurement between x2 and our landmark with a factor of 5. In your code, hard-coded, that is, go in somewhere over here where the last measurement is being applied and do the trick that I just showed you and see what the outcome is. When I do this, I get -3, 2.1, 5.714, and 6.821 as the answers. And you'll see in this final result, the final robot position of 5.714 and the landmark position of 6.821 are really close to 1 in difference, which was the measurement, because we now believe this measurement over proportionally over other measurements and motions. So here's my answer. In the omega, I replaced all the ones by 5s. So we add 5, -5, -5, and 5 over here. And also multiply the measurement by 5. If you forget this, you get a very crooked answer. You have to adjust these things over here in the same proportion as the guys over here with a 5. And that gives you the result that I stated. So now we learned all about linear graph SLAM, and that's quite a bit. And it's really simple. Every time there's a constraint, initial position, motion, or measurement, we take this constraint and add something to omega and c. And what we add is the constraint itself, but it's up multiplied by a strength factor. There's nothing else but 1 over sigma, the uncertainty in motion or in measurements. And then when we're done with this adding, we simply calculate this guy. And out comes our best possible path and along with the map of all the landmarks. Isn't that something? Isn't that really cool? So let's dive in and have you program your own real robot example. This is a fairly complicated generalization of what we just saw. I'm giving you an environment where you can specify the number of landmarks that exist, the number of time steps you want the robot to run, the world size, the measurement range, that is the range at which a robot might be able to see a landmark. If it's further away than this, it just won't see it. A motion noise, a measurement noise, and a distance parameter. The distance specifies how fast the robot moves in each step. And then I'm giving you a routine which makes the data. It takes all these parameters and it outputs a data field that contains a sequence of motions and a sequence of measurements. The code comments on the exact format of what data looks like. Now I want you to program the function SLAM that inputs the data and various important parameters, and that outputs my result, a sequence of estimated poses, the robot path, and estimated landmark positions. This is really challenging to program. It's based on the math I just gave you. The robot coordinates are now x and y coordinates. The measurements are differences in x and y. So you have to duplicate things for x and things for y. I myself put them all into one big matrix, but you can have them in 2 separate matrices if you so wish. You have to apply everything we learned so far, including the weights of 1 over measurement noise and 1 over motion noise. These happen to be equivalent in this case, but they might be different. Then you have to run SLAM and return back to me a result data structure. I'm also supplying you with the print result routine, so you can go in and see how the result has to look like. There's an example routine that doesn't work, that outputs all the correct formats, but it turns not to implement the estimate that I want you to estimate. You have to bring this to life and turn this into an amazing SLAM routine, so that when you run it, you get the same results that I do for the examples here, where there's an estimated path and estimated landmark positions. There's one last thing I want you to know is I assume the initial robot position is going to be the center of the world. So it's with the world size of 100, it's going to be 50-50, or here it's printed as 49.999, but this is the same as 50. So you have to put in a constraint that sets the initial robot pose to the center of the world. So here's my solution. I take out all the input parameters, and the very first thing is I set the dimension of the matrix and the vector, the length of the path, plus the number of landmarks, times 2, because I'm modeling x and y for each of those in the same data structures. I then create a matrix for omega and a vector for xi, give it the appropriate dimensions, and subsequently I introduce the constraint that the initial positions have to be world size over 2 with a strength value of 1. It turns out this has no bearing on the final solutions because it's the only absolute constraint. But you can see I add 1 over here in the main diagonal, 1 for x and 1 for y, and then now add the same over here. It's important to understand how I set up the data structure. There's our positions. Let me just for a second call them S. And there's our landmarks. Each of those have an x component and a y component. So what I'm doing is I'm taking this matrix and I'm setting it up not by a matrix of path length plus number of landmarks, but each of those becomes a 2 by 2 matrix where I explicitly retain the x and the y value. So the dimension here is 2 times n, the path length, plus number of landmarks. And the 2 is the result of modeling x and y, x, y, x, y, x, y. That's really important for my solution. You might have done this differently. You might have said, I'm going to build one matrix for x and one matrix for y. And then each of those becomes just a single value, which is closer to the way we discussed it in class. That's fine in this case. In general, it has disadvantages in that it cannot correlate x and y's. So for a real robot that has real rotations, this doesn't work. My solution is better, but for this specific example, this would have been perfectly fine. Coming back to my example, I now process the data. I go through all the data items, and my path index is now the data item times 2, which is the xy thing. I extract my measurements from the data, my motion from the data, using this command over here. And then I go through all the measurements, of which there might be multiple ones. I find the index in my matrix of the measurement, which is the path plus the measurement index, times 2 because we have x and y's again. And then the next routine just implements the simple addition with the measurement noise as the inverse weighting factor. So it adds 1, 1, minus 1, minus 1 to the corresponding elements in the submatrix. And in the vector, it adds the measurement, all divided by the strength of the noise variable. If you look at this carefully, it'll take a minute to digest it. I'm obviously using the auxiliary variable b to account for the fact that there's x and y. So b goes from 0 to 1. And these are all the combinations. You have to stare at them to make sure they're all correct, but I can promise you they're actually all correct. Motion is handled very much the same way. I extract the motion command. I add among the main diagonal between the two variables that are being tied together a plus 1. Then I add on the off diagonal elements minus 1s. Again, you have to stare at this very carefully to see they're all correct. And then I add the motion itself to the vector xi. That's what I had to implement. I then solve as before and return the solution. And that's exactly what's being printed out down here. I have to say, if you got this correct, I'm mightily impressed. You understood a lot about mapping and you solved a really hard programming problem. I'm responding to some of you online who ask for challenging programming problems. This is a challenging piece of code to write. It took myself a number of hours to write, and it'd be wonderful if you got it right. So congratulations. I'm impressed you made it so far. You really learned about SLAM. You learned about the map, which is a sequence of coordinates, and you learned about localization. And L and M are really the important letters here. The simultaneous and the and are not that essential. We put all of those into a big matrix omega and a vector xi. And every time we got some relative information between poses, we carved out some stuff in here. Or we measured something, we added some stuff in here and over here. These were all just additions. And as we now understand, they just implement the straightforward constraints that come from the motion and the measurements. And then the key thing was that we could solve with a simple piece of equation for the path and the map at the same time. That was quite an amazing achievement. So you've implemented this, you've implemented your first SLAM algorithm, that it goes way beyond anything I ever taught students at Stanford in a single class. Congratulations for doing this. So this is the last and final class. I'm going to output a challenge to everybody. Briefly, where you can write a robot program that puts most of the stuff we talked about together. But for now, congratulations for making it so far. That is really impressive.